Hello! In this video, we are going to prove the following theorem. The order of any element of a finite cyclic group divides the order of the group. Now, the definition of a cyclic group is as follows. Given a group G, we say that G is cyclic if G can be expressed in this form for some element A in G. In other words, we can think of this as saying there exists an element A in G such that A generates G. Now at this point, we have proven for any group element A, the order of A is equal to the order of the group generated by A. And also, we've proven the following fact, which is going to do a lot of the heavy lifting in proving this theorem. Given a group element A with order n, and given k as an integer, then the group element a to the power of k has finite order, and its order is equal to n over the GCD of n and k. Okay, so now let's get into proving this theorem. To start out the proof, let's consider a finite cyclic group, and the cyclic group is going to have this form. So we're going to say that our finite cyclic group looks like this. And since it's finite, we're going to say that the order of the group is n. Now, according to this result, we know that the order of the element A is going to be equal to the order of the group. So the order of A is equal to n. But now, we want to show that the order of any element of this group divides the order of the group. So let's consider an arbitrary element of our cyclic group. I'll call it P. Now, since P is an element of this group, well, what does this mean? It means that P is equal to a to the power of some integer. I'm going to call that integer k. But now, according to this result, since we know that the order of our group element A is equal to n, well then, a to the power of k must have finite order, and the order of a to the power of k is equal to n over GCD of n and k. Now I'm going to call this result star, just for reference. And since p is equal to a to the k, we know that this is equal to the order of p. But this quantity divides n. Because what does it mean for n over GCD of n and k to divide n? It means that there exists some integer x such that n over GCD of n and k times x is equal to n. In fact, we know that there exists an integer x that satisfies this. Just take x to be the GCD of n and k. So indeed, this is true, so we can conclude that n over GCD of n and k divides n. And n is the order of our group. So this shows that the order of P divides the order of our group. So putting this all together now, we considered a finite cyclic group, and we have shown, given any element of our finite cyclic group, the order of that element divides the order of the group. And that is exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.